Okay, so let me recall the space of test functions this is d of omega. So omega in Rn open set, d omega is set of all phi from omega to R such that phi is C infinity and support of phi contained in omega compact. This is a vector space with the usual pointwise addition and scalar multiplication, and we have seen that it is very well endowed. There are lots of functions which we can construct with specified properties. So we now want to, so let me also recall that support of phi is nothing but set of all x in omega such that phi x is different from 0, and then you take the closure. So it's always a closed set, and if it is compact then you say it's a function with compact support. Okay, so now we want to give a topology on this space. Okay, so the topology which we are going to give is called the inductive limit topology. I don't want to give the details of this topology. Again, you can read it from the book which I cited before, Topics in Functional Analysis Applications, and it doesn't really matter for us. What we want to know is that this topology, which makes d omega into a topological vector space, is in fact it is for purpose of continuity, it is enough to deal with sequences. So that is the nice property of this topology, and therefore it is enough to know when a sequence in d omega is convergent. So enough to know when a sequence phi n in d omega is convergent. Okay, so this is all that we know, and therefore we want to know, since it's a vector space, it is enough to know when it converges to 0, because if phi n converges to phi, then phi n minus phi converges to 0, and therefore it is enough to know when the sequence is convergent. So definition, okay, a sequence phi n in d omega is said to converge to 0, to the 0 function, okay, if and only if there exists a fixed compact set K contained in omega such that support of phi n is contained in K for all n, and phi n and all its derived sequences converge uniformly to 0 on K. Okay, so this is the definition. So what do we mean by derived sequences? So let us take, for instance, in one dimension, if n equals 1, so if you have omega contained in R, that means let's say an interval, so you have phi n is a sequence, and then you have phi n dash is a sequence, then phi n double dash is a sequence, and so on, and then phi n kth derivative gives you another sequence. So these are all the derived sequences. All of them must converge uniformly to 0 on this compact set. So if you have higher dimensions, then you think of sequences got by all kinds of partial derivatives. Every one of them has to converge to 0. So this is a very costly condition. So lots of things have to happen in order that a sequence phi n goes to 0 in d omega. Okay, so with this we can, so this is the topology, and now we have a topological vector space, and as I said, continuity on this topological vector space for linear functionals is dependent only on behavior of sequences. Therefore, well, you know, generally in a topological space, except in metric spaces, you cannot say continuity characterizes the entire topology, but in this case it is so happens that you can do it here also. So the dual space of this is called the space of distribution. So we have the next definition. A continuous linear functional on d omega is called a distribution on omega. Okay, and so T is a distribution if it's T means d omega to r is a linear functional, and phi n going to 0 in d of omega implies t of phi n, which is now a real number, goes to 0. So this is the condition for a distribution. Okay, so this is what we mean. So the space of all distributions on omega is denoted, so it's a dual space, so we are going to denote it by the usual symbol d prime of omega. So now we want to give a lot of examples of distributions, and of course the first is to redeem our promise that we wanted to generalize the notion of a function to a distribution. So we want to know what functions can be considered as distributions, and then we show that it's a more general thing. So we have one more definition now. So omega in Rn, it's an open set, a real valued function. So as I said, complex valued is also fine if you are dealing with complex things, but we are going to deal with reals most of the time, and it's all applicable to complex valued functions, is said to be locally integrable if and only if for every k contained in omega, k compact, we have integral of mod f dx over k is finite. So this integral f is a function which is defined on omega, and modulus of f should be integrable over every compact set. That means this integral has to be finite. Then you say the function is locally integrable. So if you have any continuous function is locally integrable. So because any continuous function on any compact set is bounded, and compact sets have finite Lebesgue measure, and therefore this integral is always finite. Any LP function is locally integrable, because if you have a function which is in LP, then it is in LP of any compact set also, and if your compact sets are finite measures, so if it is LP in a compact set, then it's also L1 in a compact set. So this is 1 less than equal to P less than equal to infinity, and therefore again these are all locally integrable. So let us give another example of a function which is not covered by these two examples. So let us take omega equals R2, so example, and then you take f of x equals 1 over mod x where x is not equal to 0. So it's only defined away from the origin. and we want to show this is not a continuous function, and it is not L1 function, LP function, because at the origin you have a problem, and therefore you want to show that this is locally integrable. Now, why is this this blows up at the origin? Okay, so why is it locally integrable? Well, if you take any compact set K which does not contain the origin, then of course this is a nice continuous function, and therefore the integral will be automatically finite. So enough to check integrability near the origin. So you take B, which is a ball, center 0, and say, let us say radius A is positive. So this is the ball, center, origin, and radius A, and we want to look at integral over mod x less than or equal to A of 1 over mod x dx. Okay, and so we are now going to use polar coordinates, and therefore this is equal to integral 0 to A of, and integral 0 to 2 pi. Then you have r dr d theta. That is how the dx1 dx2 will change when you change to polar coordinates, and then you have the function which is itself 1 by r, where r equals mod x. Okay, and now you see that this r gets cancelled, and therefore this just gives you 2 pi a, which is finite, and therefore you have that this function is a locally integrable function. Similarly, you can construct in higher dimensions also locally integrable functions, like in R3 1 by mod x square will be locally integrable, and so on. So now we are going to give the first example of a distribution. So omega contained in Rn open set, and F locally integrable defined on omega. So our notation for this will be F belongs to L1 loc omega. So this is locally integrable is abbreviated to this notation. Okay, so now we are going to define Tf from d omega to r, defined by Tf. So you have to define what is its action for every phi in d omega. So I am going to define this is equal to integral on omega f phi dx. Okay, so we have to check that this is a distribution. So first of all, well defined, because you have Tf of phi modulus is equal to integral omega, but it is enough to take it over the support of phi, because outside the support of phi is 0, and this is a compact set. So this is f phi dx in modulus. This is less than or equal to norm phi infinity, that is the sup of this function or the max of this function over the compact set support of phi into integral of mod f support of phi. And now this is a compact set, and you know that this quantity is finite. Okay, and this is also finite, and therefore mod Tf of phi is a finite number, so it is well defined, it is also linear. So that is why we need locally integrable functions, so that you have that this is well defined. Okay, you cannot define it otherwise unless the function is integrable over any compact set. Now we have to check continuity. So let phi n, so continuity, converge to 0 in d omega. So we have to show Tf phi n goes to 0. Okay, so but now again the same thing will hold. So Tf phi n in modulus is less than or equal to norm phi n infinity into integral over k mod f dx, where support of phi n are all contained in a fixed compact set k. So phi n goes to 0. So by the definition of the convergence to 0, all the supports are contained in a fixed compact set K. So this integral, which was supposed to be over the support of phi n, is now we are enlarging it to a bigger set, namely over K, and this quantity is a fixed finite quantity here. And you know that phi n goes to 0, so on K all these phi n's will go to 0 uniformly, and therefore this goes to 0. Norm uniformly means norm phi n infinity goes to 0, and therefore this, so therefore TF of phi defines a distribution. So now we are going to state a proposition. Let f belong to L1 log of omega. So omega is in Rn an open set and f is a locally integrable function, and assume that for every phi in d omega we have integral f phi equal to 0. Then f equal to 0 almost everywhere. Okay, so proof, we'll do it in two steps. So the first step, we assume that f belongs to L1 of omega, that is, it is integrable on entire omega, not just locally integrable, and that measure of omega, this is the mod omega means the Lebesgue measure of omega is finite. So it's a set of finite measures. Okay, so let epsilon be greater than or equal to 0. Then there exists f1 in d of omega such that integral on omega mod f minus f1 is dx is less than epsilon. So this, that is, d omega is dense in L1 of omega. So we are using this fact. We will prove this a little later. So we I think it is known, if you have done some measure theory or functional analysis, you would have seen continuous functions with compact support are dense in any LP space other than L infinity. In the same way, C infinity functions with compact support are also dense, and we will definitely prove this a little later. For the moment, we will just assume this fact. Okay, so then let us take phi in d omega, and then if you have integral on omega f1 of phi. So this is equal to integral on omega f1 minus f of phi dx, because integral f phi dx is 0. So I have just added 0. So this is, and that is of course less than epsilon times norm phi infinity. Okay. So now you set k1 to be set of all x in omega such that f1x is greater than or equal to epsilon, and k2 equals set of all x in omega such that f1x is less than or equal to minus epsilon. Okay. So now recall, f1 has compact support. So this implies that k1 and k2 are disjoint compact sets contained in omega. Okay, so then we have, I gave you an exercise last time. So there, there exists a h in d of omega such that h is identically 1 on k1 and h is identically equal to minus 1 on k2, and mod hx is less than or equal to 1. Okay. So if you take k equals k1 union K2. This is again a compact set. Then you have that integral omega f1 of h equals integral omega minus k of f1h dx. I keep forgetting the dx. Okay, plus integral k f1h dx. I am just splitting the thing. So now if you take integral on k mod f1 dx, this is nothing but on k, what is k? K is where f1 is negative or positive, and therefore this is equal to integral over k f1h, because on k1 f1 is positive and h is 1, on k2 f1 is negative and h is minus 1. So f1h is precisely mod f1 on k dx. Okay, and that is less than or equal to, from what we just saw earlier, from this condition you have that is, it is less than or equal to epsilon plus integral on omega minus k of mod f1h. And mod h is less than or equal to 1, so this can be written as less than epsilon plus integral on omega minus k of mod f1 dx. Okay, but on omega minus k, what do we have? We have mod f1 of x is less than or equal to strictly less than epsilon. Okay, and therefore we have that integral on omega mod f1 dx is equal to integral on k mod f1 dx plus integral on omega minus k mod f1 dx. The first one we just estimated, that is less than or equal to epsilon plus twice integral omega minus k mod f1 dx, and that is less than or equal to epsilon plus 2 epsilon times mod of omega minus k, which I will write less than or equal to mod of omega. And therefore it follows that integral over omega of mod f dx is less than or equal to integral over omega mod f minus f1 dx plus integral on omega mod f1 dx. And we have just computed the second one. So this is, first one is less than epsilon, we already know. This is less than epsilon plus 2 epsilon mod omega. So this is less than 2 epsilon plus 2 epsilon times mod omega. And this can be made, of course, arbitrarily small. So epsilon arbitrarily small implies integral omega mod f dx equal to 0, and this implies that f equal to 0 almost everywhere. So we have proved this in the case when f is an integrable function on omega and omega has finite measure. But if omega, so step 2, omega arbitrary open set, then you can write omega as the increasing union. So union n equals 1 to infinity omega n, where omega n is an increasing sequence of relatively compact sets, open sets, relatively compact open sets. So what is the example? For example, you take omega n to be equal to set of all x in omega such that the distance of x from Rn minus omega is bigger than 1 by n, and then you intersect it with the ball center 0 and radius n. So omega is some open set, and then you take the ball center origin and radius n, okay, and also you take the sets which are greater than 1 by n from the boundary of omega. Okay, so we are really looking at these sets. and as n increases, the ball becomes bigger and bigger. It will ultimately cover the whole of Rn, and therefore you will be able to write x in this fashion. Okay, and these are okay. So now by step 1, since integral f phi is 0 for every phi which is in d omega, it is also true for d of omega n, and therefore f restricted to omega n equal to 0 almost everywhere. Now that means f is 0 except on a set of measures 0 in omega n, and now countable union of sets of measures 0 is of measure 0. So this implies that f equal to 0 almost everywhere in omega also. So what does this proposition tell us? So in view of this proposition, so remark, in view of this proposition, if f and g are in L1 log omega, and if Tf equal to Tg, that is integral f phi over omega dx equals integral g phi over omega dx, this implies that f minus g equal to 0 almost everywhere, that is f equal to g almost everywhere. And when you are looking at measurable functions, equality almost everywhere, especially integrable functions and so on, equality almost everywhere is enough, and therefore they are essentially the same function, and therefore there is, so this implies there exists a one-to-one correspondence between elements of L1 log omega and the distributions they generate. So from f to Tf, this is a bijection. Okay, so in future I may, if necessary, I will say Tf to be absolutely clear if there is a reason for confusion. Otherwise we will just say the distribution itself is f. So when I say a function is a distribution, I mean a function f in L1 log omega is a distribution, means we are looking, that is we are looking at the functional phi going to integral f phi dx. Okay, so and this is, gives you a one-to-one correspondence between the functions. So the function is well defined. So therefore this is how we generalize the notion of a function. A locally integrable function can be thought of as a distribution. Okay, so we will now continue other examples of distributions.